Hello students, welcome to Educate. Today we are going to start next chapter of class 11th physics, that is thermal properties of matter. It is chapter number 10. So here the basic point is temperature and heat. You know temperature is degree of hotness or coldness, and heat also it is a type of energy. Now considering the units of heat and temperature, so you have already studied about the unit of heat. Heat is measured in joule and temperature is measured either in Kelvin or in degree Fahrenheit or in degree centigrade. Now we are going to see how these scales are related. So for this purpose we need fixed points. So what are the fixed points here? So we draw three scales, and this point is called lower fixed point, at which ice melts, right? So this scale is degree centigrade, this is degree Fahrenheit, and this is Kelvin scale, right? So this is 0. In degree Fahrenheit it is 32, and in Kelvin it is 273. Now this is upper fixed point. So here, as name suggests, degree centigrade. Grade means division, centi means 100. So there are 100 divisions in it. Here there are 180 divisions. Here there are 100 divisions. Now if you add 0 to 100, you will get 100 here. If you add 180 to 32, you will get 212. If you add 100 to 273, you will get 373. Right? Now what is relation? The relation is name of scale minus lower fixed point divided by divisions equal to constant. Correct? Scale name, then lower fixed point divided by number of divisions equal to constant. So here we can write like C, lower fixed point is 0. So I am not writing. Number of divisions are 100 equal to name of scale is Fahrenheit. Its lower fixed point is 32. Number of divisions are 180. Then Kelvin scale, lower fixed point is 273 and number of divisions are 100. Right? So this is the relation between three scales. Now taking any two, suppose you take C upon 100 equal to F minus 32 divided by 180, or C equal to 100 divided by 180 times F minus 32. Is it okay? 100 is taken here. Now let's simplify. C equal to here 5 upon 9 times F minus 32. Right? So this is a relation that relates degree centigrade and Fahrenheit. For example, suppose F equal to say 40 degree F. So what is degree centigrade? So put the value of F here. So C will be 5 upon 9 times 40 minus 32. So you will get 8 from here. So 5 into 8 divided by 9 degree centigrade. Take another example. Suppose if you write say F equal to say 120 degree F. Then what is C? Degree C value. Then again same formula, C equal to 5 by 9. In place of this F, you are going to write 120 and minus 32. Then evaluate it, you will get the value in degree centigrade. Now we are going to see another example. So what you have seen, C upon 100 equal to F minus 32 upon 180, right? Now reverse case, suppose you want to convert degree centigrade into F, either you can put direct value and then cross multiply, or if you want to relate, if you want simplified formula, you can do that also. So it will be F minus 32 equal to 180 divided by 100 C, right? This will cancel out 1.8. So F minus 32 is 1.8 times C, or F equal to 32 plus 1.8 times C. So this is basic relation. Now suppose you are given centigrade values. So suppose given temperature is say 25 degrees centigrade and you need corresponding Fahrenheit value. So what you do? So F is equal to 32 plus 1.8 times 25. Simplify it, you will get degree Fahrenheit value. Now there is one question. What is the temperature whose value is same? Question is, what is the temperature whose value is same in degree C and degree F? Try this. Take 1 minute to think, then I will tell. Question is, what is the temperature whose value is same in degree centigrade and degree Fahrenheit? So formula you know, C upon 100 is equal to F minus 32 divided by 180, right? Here question says temperature should be same. So let F equal to C equal to X. So if we write here X upon 100 equal to X minus 32 upon 180, right? So let's simplify. 180x equal to 100x minus 32 100. Here this will become 80x equal to minus 3200. So x equal to minus 40, right? So you can say minus 40 degrees centigrade is same as minus 40 degree Fahrenheit, right? This is good question. Now there was a relation C upon 100 F minus 32 divided by 180 is equal to K minus 273 divided by 100. Suppose you want to relate these two. So you will write C upon 100 equal to K minus 273 divided by 100. So 100 will cancel out. C equal to K minus 273 or K equal to C plus 273. So suppose you want to convert degree centigrade into Kelvin, then add directly 273. You will get the answer. Or if you want to do just reverse, means centigrade value you want to find out from Kelvin. So C will be equal to K minus 273. So these relations will make the conversion of one scale into another easier. So you will be able to convert any temperature. If degree centigrade is given, you can convert it into degree Fahrenheit or Kelvin or any. So I think you have understood the basics. Now here graph is shown, and through graph also a plot of Fahrenheit temperature TF versus Celsius temperature is shown here. So what they want to tell you, 212 degree Fahrenheit and here 100 degree centigrade, or 0 degree centigrade and 32 degree Fahrenheit, both are equal. So that thing is given here. Here same thing is written, that TF minus 32. So Fahrenheit temperature minus 32 lower fixed point divided by number of divisions. So number of divisions are 180, and then TC temperature scale here degree centigrade, its a lower fixed point will be 0, that is why not written, divided by 100. So same relations there. Here Kelvin is not involved, but you have already studied, so you will understand it easily. Now here there are some important laws in this para. You will find all laws possible. So let's see one by one. Liquid in glass thermometers show different readings for temperatures other than the fixed points because of differing expansion properties. A thermometer that uses a gas, however, gives the same reading regardless of which gas is used. Experiments show that all gases at low densities exhibit same expansion behavior. The variables that describe the behavior of a given quantity or mass of a gas are pressure, volume, and temperature. Three things are there. They are important. And PVT, where T equal to T plus 273.15. We will study why this 273.15. When temperature is held constant, here we are going to study first law, that is Boyle's law. Boyle's law says when temperature is held constant, the pressure and volume of a quantity of gas are related by this relation. So product of pressure and volume remains constant. So this is PV equal to constant. This is Boyle's law. Then here Robert Boyle, the English chemist who discovered when the pressure is held constant. Now in previous case, when temperature is held constant. Now in this case, when the pressure is held constant, the volume of a quantity of gas is related by the relation V upon T equal to constant. Right? This is second law. This is called Charles' law after French scientist Jacques Charles, 1747-1823. Now, low density gases obey these laws, which may be combined into a single equation. So let's see. Here, graph between temperature and pressure is shown. So what happens? At minus 273.15 degrees centigrade, although this is extrapolated, it means this is just expected. Graph was like this. From here, this is drawn without measuring exact values. But considering the tendency that it should be straight line, so it is meeting the temperature axis at minus 273.15 degrees centigrade. At this temperature, volume of the gas becomes 0, right? So this is taken as absolute 0. Here pressure and the temperature graph is shown, again same thing, but here gases are taken, means different gases are taken, but despite that, at the same temperature, minus 273.15 degrees centigrade, here volume becomes 0, pressure becomes 0, right? If pressure is 0, it means there is no volume. So this is called absolute 0, correct? A plot of pressure versus temperature, extrapolation, again extrapolation means practically to certain extent they reached, and after that, considering the tendency, they have extended the line. So that cuts this temperature axis at this point. So this temperature is called absolute 0. Here relations, notice that since PV equal to constant we have seen and V upon T equal to constant also we have seen, then PV upon T, if we combine the two, PV upon T should also be constant. This relationship is known as ideal gas law. Understood? Two laws are being combined here. The first one was PV equal to constant, and second law was V upon T equal to constant, right? So here we can say PV upon T, PV upon T equal to constant. Now we have to determine what constant we can put. So here we can put mu r, right? So it can be written in a more general form that applies not just to a given quantity of a single gas but to any quantity of any low density gas, and is known as ideal gas equation. So further we write it PV upon T equal to mu r or PV equal to mu RT, right? Up to here there is no problem. PV equal to mu r or PV upon T or PV equal to mu RT, where R is universal gas constant and its value is 8.31 joule per mole per Kelvin, right? Here some interpretation is given, and then absolute zero concept, as I told you, where volume becomes zero, pressure becomes zero. So that concept is given. Here the same thing that we have discussed in the beginning, different temperatures are given, like 0 degree, 100 degree, 32 degree Fahrenheit, 212 degree Fahrenheit, then here 273.15. So here generally we take 273 and then gap of 100. Here it is taken 273.15. This is more accurate, and then 100 if you add you will reach here 373.15, right? So size of here there is one important point. The size of unit in Kelvin and Celsius temperature scale is same because gap is same, as you know. Here there is gap of 100, here gap is 100, but here gap is 180. So size of the unit in this will differ. So there will be one numerical based on this size, we will see that. And here this, to convert temperature of degree centigrade into Kelvin, we have to add this value, the gap, the lower fixed point. We have already studied about this. Now we are going to see what is thermal expansion. So thermal expansion means when metal is heated, then what happens? It will expand. So that expansion is called thermal expansion, or expansion due to temperature. When heat is given, then there will be expansion. So that we are going to study through a formula. So we can say that suppose initial length, in terms of length we are going to say initial length is equal to say L. Temperature difference, say delta T, right? So we say that initial length is proportional to what? So expansion, here we can say that initial length, or just you can write increase in length depends on what factors. So actual formula is L equal to L01 plus alpha delta T, right? So let's see on what factors it is depending. So we can generalize it. So L equal to L0. So here initial temperature, the initial length is taken as L0, temperature difference is taken as delta T, and alpha is temperature coefficient. So L equal to L0 plus L0 times alpha delta T, right? Take L0 to this side. So L minus L0 equal to L0 alpha delta T. So the thing that I wanted to state in the beginning, so same thing we can write here. So change in length delta L proportional to original length L0. Change in length is proportional to temperature difference, right? So if we include these two together, then delta L proportional to L0 and delta T, or generally temperature should be written like delta capital T, right? If by mistake I write, but you have to be careful. So it represents temperature, right? So here delta L will be equal to a constant alpha, then L0 delta T. The same thing is written here in this form, expanded form. I think you have understood, or if you need quick recap, so I'm telling you. So L equal to L0 1 plus alpha delta T, right? If you open it, you will get L0 plus L0 alpha delta T, or L minus L0 equal to L0 alpha delta T. This can be written as delta L equal to L0 alpha delta T, right? So this is basic relation. Here we can say proportionality like this: delta L proportional to L0, delta L proportional to delta T, right? And here alpha is temperature coefficient. Now what is that and what is its unit? See, if you consider the principle of homogeneity, so every term must have same unit. Here one has no unit. It means alpha delta T must be dimensionless. So alpha delta T is say 1. So unit of alpha will be 1 upon delta T, that of temperature. So you can say Kelvin minus 1 or degree centigrade minus 1. So anyone can be taken, that depends on context, right? So you have understood. So this was concept of linear expansion. Here same thing is given. Then we consider expansion in area, superficial expansion. The same thing is true. A equal to A0 1 plus beta delta T, right? Here this is initial area, or if we open the bracket, A0 plus A0 beta delta T, A minus A0 equal to A0 beta delta T, or delta A equal to A0 beta delta T, or we can say change in area proportional to original area. Change in area is proportional to temperature difference, right? Here beta is coefficient of superficial expansion and unit will be same as that of alpha. Then comes cubical expansion or volumetric expansion. So again we can say that if V is new volume, original volume is V0, so 1 plus gamma delta T, right? Where gamma is coefficient of cubical expansion. So we can open the bracket, V0 plus V0 gamma delta T. Now V minus V0 equal to V0 gamma delta T, or delta V equal to V0 gamma delta T. So we can say that delta V is proportional to V0, delta V is proportional to delta T, right? Now, how are the coefficients related? So relation is simple. Alpha upon 1 equal to beta upon 2 equal to gamma upon 3. So this relation will hold anywhere. Here another thing is given here, like delta V upon V of a substance for temperature change delta T, and define the coefficient of volume expansion for. So here it is defined. We can find the term that we have used as gamma. So they have written as alpha V. So in case of superficial expansion, they will write it as alpha and then A for area. So that is okay. That does not matter. So you have understood the basic concepts. Here, coefficient of volume expansion of copper as a function of temperature. So graph is shown. So here this is gamma or alpha times V. So graph varies like this. So you can say that with increase in temperature, gamma also increases, but not linearly. Here in the table you will find different values of gamma. Then we are going to see the anomalous behavior of water. What does this mean? Anomalous behavior of water means, here through graph you can understand, water has the maximum density at 4 degrees centigrade, right? So here you can see density is 1000 kg per meter cube. This temperature corresponds to 4 degrees centigrade. Below or after, it decreases. Here the same is given. This is volume of 1 kg of water. So this at 4 degree, it is lowest, right? And then it will increase, correct? So you have understood this is called anomalous behavior of water. You can read about it. It's a simple. Here, as a lake cools toward 4 degrees centigrade, water near the surface loses energy to the atmosphere, becomes denser and sinks. The warmer, less dense water near the bottom rises. However, once the colder water on the top reaches temperature below 4 degrees centigrade, it becomes less dense and remains at the surface, where it freezes. If water did not have this property, then what would happen? Lakes and ponds would freeze from the bottom up, which would destroy much of their animal and plant life. You have understood? Upper surface, upper surface freezes, whereas lower surface remain in liquid form. That is why that is necessary for survival of the aquatic life and plant life. So that is one important property. Here some basic points are also given. You can see gases at ordinary temperature expand more than solids and liquids. For liquids, the coefficient of volume expansion is relatively independent of the temperature. However, for gases, it is dependent on temperature. For an ideal gas, the coefficient of volume expansion at constant pressure can be found from the ideal gas relation here. PV equal to mu RT. Let's see how. So PV equal to mu RT. Here, if we differentiate, assuming that P constant, mu constant, R constant, only these two quantities can change. So we write P delta V, or we consider the change. So mu R times delta T. And our concern is to find, our concern is to find delta V upon V. So if we divide this equation number 2, this is equation number 1. Sorry. This is equation number 1, this is equation number 2. If we divide the two, P delta V divided by PV is equal to mu R delta T divided by mu RT. So what do you get? Delta V upon delta T, sorry, delta V upon V is equal to, from here you will get delta T upon T, right? And if you remember formula, when we have written V equal to V0 1 plus gamma delta t, and then we simplify it, so V minus V0 equal to V0 times gamma delta t, then this is delta V, and this is say V0, so here we write V0, although delta V upon V same thing, equal to, what do we get here? This is gamma times delta t, right? So here if you compare gamma times delta t, here delta t upon t, so you can say gamma and t both are equal, inverse relation, so we write gamma equal to 1 upon t. The same thing they are writing here, in place of gamma they have written alpha, then they put V as subscript, volume, right? And this is cubical, coefficient of cubical expansion, this is also coefficient of cubical expansion, so 1 upon t. So here at 0 degree centigrade, alpha, this for volume is 3.7 into 10 power minus 3 Kelvin, which is much larger than that of that for solid and liquid. And here you have seen the graph. Here those relations are given, as I told you that the first one linear expansion coefficient was taken, then volumetric. So if you wish, I can tell you this also in simple terms. You know, there is a simple relation between coefficient of volume expansion gamma or alpha times V and coefficient of linear expansion alpha. Imagine a cube of length L that expands equally in all direction, then its temperature, when its temperature increases by delta T. So what is happening? In while finding alpha, we use one simple length, right? And we write the relation L equal to L0 1 plus alpha delta T, right? But when you are considering a cube, then all three dimensions will experience the increment. So in that case, volume expansion will take place. So each side will increase by certain amount. So that increment will be written, and then if we make it cube, then we will get certain relation. So here the same thing is given. The first thing they have written delta L equal to alpha 1 L delta T. That relation, if you remember, that delta L equal to we generally use L0 alpha delta T, right? The same thing is written here. Then in case of volume, so delta V means suppose size changes by delta L, so L plus delta L whole cube minus original volume L cube. So we can simplify it, and then we will get it almost equal to 3 times L square times delta L after simplified. Why so? If you wish to know, so let's explain it, that will be better. So delta L, you have seen that it is alpha times L delta T. This is first relation, right? And now we are considering change in volume. So new side is L plus delta L whole cube minus original volume was L cube. If we open the bracket, what is formula? A plus B whole cube, A cube plus B cube, L cube plus delta L cube plus 3L square delta L plus 3L delta L square minus L cube, right? So L cube will cancel out, and delta L is very small, right? If delta L is small, then its higher powers like this or like this will be too small. So we can neglect them. Then what is left? So this thing will be left 3L square delta L. So change in volume, we can write delta V, we have got 3L square delta L. right? Now, suppose we want to convert this L square into volume, means L cube. So we can do one thing, we multiply L and divide by L. So this will become 3L cube, right? Delta L upon L. This is delta V, correct? So we can write it as 3 times this is volume and delta L upon L, correct? And if you remember here, if you find delta L upon L, so what will it be? Delta L upon L will be alpha times delta T, right? So here delta L upon L is there, and V we can take a denominator, so we will get delta V upon V. Here will be 3 times delta L upon L, and delta V upon V will be gamma, which can also be written as alpha with subscript V equal to 3 times this is alpha, or alpha length, correct? So this is the relation. Similarly, we can relate beta also, but that is not given in your syllabus now. Earlier it was there. So what happens by preventing the thermal expansion of a rod by fixing its ends rigidly? Here there is one important point, that suppose this rod is fixed between these two, this is rod and these are two fixed, say, walls, between them it is fixed and now it is heated. What will happen? Definitely there will be expansion. So that will be called thermal stress, because in this side it will expand, in this side this will, and it will not be allowed. If it is free, means suppose this is rod and it is being heated and it is free to expand, then there won't be any thermal stress. But in this case, since there is restriction, so definitely there will be some thermal stress. So that thing they are talking here. So let's see what is written. What happens by preventing the thermal expansion of a rod by fixing its ends rigidly? Clearly, the rod acquires a compressive strain due to the external forces provided by the rigid support at the ends. The corresponding stress set up in the rod is called thermal stress. For example, consider a steel rail of length 5 meter and area of cross section 40 centimeters square that is prevented from expanding while the temperature rises by 10 degrees centigrade. Of course, so there will be expansion. The coefficient of linear expansion is given. So we can find delta L upon L by putting the value. This will be 1.2 into 10 power minus 4. Young modulus of steel is this much, 2 into 10 power 11. And you know, stress is given by force upon area. So force upon area we can evaluate. So that will be equal to, I think I should write it here so that you can recall easily. What is Young modulus? Force upon area divided by delta L upon L, where this is strain, this is stress. The same concept is being used. We want F upon A, so F upon A we can write then Y times delta L upon L. So, and you know delta L upon L, that is alpha times temperature difference, so that value we can write here. So Y steel into delta L upon L, we get this, which is correspond to external force. So delta F, if you want to find out, then you multiply by area. So this much force will be there. If two such steel rails fixed at their outer ends are in contact at inner ends, a force of this magnitude can easily bend the rails, obviously. So in this lecture, we will end at this point. In next lecture, we will continue. Thank you. Team Educate.